This lecture is about upwinding for ut plus aux is equal to 0. So we know that the skin 1, which is, if we discretize ut by forward Euler and ux by d0, 2h uj plus 1n minus uj minus 1n is equal to 0. That's no good. Okay, the natural question is, what about d plus and d minus? Okay. In other words, what if we discretize ux by uj plus 1 minus uj divided by h, or uj minus 1 divided by h? Right? So the first question is, which one? Which one should we adopt? If we write the skin down in terms of uj n minus 1 is equal to what? Alright, so that is uj n minus a delta t divided by h, uj plus 1n minus ujn, right? Or ujn plus 1 is equal to ujn minus a delta t over h, ujn minus uj minus 1n. Okay? So if you take a good look, here so ujn plus 1 is in terms of ujn and uj plus 1n. Right? Here is in terms of ujn and uj minus 1n. So the question becomes, if we were to choose between these two, the question becomes, should ujn plus 1 depend on uj plus 1n or uj minus 1n? Okay. So we go back to the phenomenon that is modeled by the PDE, by the equation, and see which one should be a physically correct choice. Okay, that's the key. So we go back to physics, to what the equation models. In our setting, that's the so-called characteristics. That's what we discussed when we started this section. Okay, so remember, what this equation models is a transport. If we follow the characteristics at x0, all right, and here is xt. Here, let's say it's j, xj, here is tn plus 1, all right? This function value should be equal to the function value at x0 and time 0, with this slope being the slope of this characteristic line being 1 over a, right? This is 1, that's a. Remember, we want dx dt is equal to A. Okay, so this thing becomes total derivative. We go to revisit the earlier video. So the total derivative with respect to t is 0. So the function is constant with respect to t, right? So it doesn't depend on the time. Time at tn plus 1 is equal to function value at time 0. So then it's pretty clear that we have some sort of a wind direction, right? That's what we alluded to in the earlier video also. So think of this transport as a wind. The wind is blowing. The wind is blowing from left to right when A is larger than 0, right? And it is blowing from right to left when A is less than 0. Okay, so in that case, it's something like this. Okay. So that means this direction means that when A is larger than 0, the information is coming from the left, right? From left. Wind is blowing from left to right, from the left, which means Ujn plus 1 is dependent on Uj minus 1, not Uj plus 1 if we have to choose between these two. Okay? When A is less than 0, we know this Ujn plus 1 depends on Uj plus 1 and not Uj minus 1 n. Okay? That's a basic observation. Moreover, from this observation, we can derive the condition on delta t. So if you let's plot this again, we have here is Tn plus 1. Here is Tn, okay, and we have the point value here. Here is xj plus 1, and maybe here is xj, right? So what we do is that so we discuss a case where A is larger than 0. What we do is that we're going to use a linear combination of these 2 points, right? If you think about it, we can rewrite it. The scheme is, so when A is larger than 0, you should use Uj minus 1. So the scheme is Ujn plus 1 is equal to 1 minus A delta t over h Ujn, right, plus A delta t over h Uj minus 1 n. So it's a linear combination of these two, right? So this between these two, it determines the value at j plus 1, at j n plus 1. So this should be j, and this is j minus 1, okay? So if you follow the characteristics and you ended up at here, which is this guy is delta t. What's that? This guy is A delta t. Okay, A delta t. And the exact solution, the exact physics leads us to this location, this black dots. Okay. If you give that a name, let's say let's call that C. Here is A and B. So C should be within A and B. Otherwise, it's not physical. So we are determining Jn plus 1 by the linear combination of A and B. Of course, it's just an intuitive derivation. If the condition of this condition means that our A delta T should be less than H. Okay, so we arrive at the same A delta T over H should be less than 1. So this is the same condition as Lex Friedrichs, Lex Windroff, and also the leapfrog. Okay, same condition for the scheme 2, 3, 4. In general, that's the case when A is larger than 0, right? In general, A, which is for any A, we have this absolute value A delta T over H is less than 1. Perhaps a slightly more rigorous approach to view this, another perspective to view this, is through interpolation. Okay. The same picture we just drew. So what we have is that, well, we want Ujm plus 1. This is approximation to the exact solution U at xj tm plus 1. Okay, and we know this is this location. Okay, this location, we know this is equal to U, the exact solution. We trace the characteristic back to Tn. So that's U xj. Again, we should subtract A delta T. Alright, and we go back to time level Tn from Tn plus 1. And what the scheme does, so that's the location C, all right? So what the scheme does, the scheme does is to interpolate Uj minus 1n and Ujn for U xj minus A delta T Tn. So, for example, we can do a linear interpolation. Right? If we do linear interpolation, so the U xj minus A delta T Tn, alright, Tn, we come up with a linear function, alright, a linear function that approximates. So this is a straightforward yet potentially a little bit tricky. So we come up with a linear function, straight line, right? We come up with a linear function with respect to x, okay, and it should be equal to Uj minus 1n when x is equal to xj minus 1, and it should be equal to Ujn when x equal to xj. A quick way to write this down is use a point slope. Okay, the slope is Ujn minus Uj minus 1n divided by h. Rise over round, okay? Point slope form. X minus xj minus 1. All right. Again, what this is that this is a linear interpolant of ux at Tn between xj minus 1 and xj, a linear interpolant. When x equal to xj minus 1, the second term is 0, so you get a uj minus 1n. When x is xj, you get h here, h cancels the h, you get a ujn, alright? So it exactly interpolates at these 2 points. So that's a linear interpolation of these 2 points, but of course we're looking for xj minus a delta t, so you need to evaluate, okay? You have this variable x, you just evaluate this x at equal to xj minus a delta t. Okay, because we started out by looking for a value at a particular location. So you shouldn't just give me a function. You should evaluate that function at that location. Okay? So what's that? That's just uj minus 1n plus the slope ujn minus uj minus 1n divided by h times xj minus a delta t minus xj minus 1. Alright, so we know xj minus xj minus 1, which is uj minus 1n plus ujn minus uj minus 1n divided by h. We get h minus a delta t. If you simplify, you see this is just ujn, right? This h and this h cancel. You have ujn minus uj minus 1n plus uj minus 1n. You get ujn, right? And then what we have left is a delta t over h ujn minus uj minus 1n. You see this is exactly the same. That's the exact upwinding scheme for a is larger than 0. Okay, so this is really a good choice, because this is equivalent to doing a linear interpolation of the exact solution, right? You're doing a linear interpolation of the exact solution. So let me offer a third perspective to further look at these schemes. It's a very important scheme. A third perspective is through stability. Okay, stability. So what we have is that, again, let's just look at the case A is larger than 0. The other case is equivalent. That means the derivation is the same. We have ujn plus 1 is equal to ujn minus a delta t over h ujn minus ujn minus 1n. Okay? If we follow the form of the equation, this ujn plus 1 minus ujn divided by delta t, that's ut, is equal to negative a ux, right? Negative a ux. It's uj n minus uj minus 1n divided by h. So if we remember for the Lex Friedrichs, Lex Windroff, we viewed that as a correction to the centered scheme, which is uj plus 1n minus uj minus 1 divided by 2h. Alright? And I'm going to add that because this is plus a uj plus 1n minus uj minus 1n divided by 2h. And then we have this original guy back. H uj minus 1, ujn minus uj minus 1n. Alright? So this is that d0, okay, uj minus 1, uj plus 1n minus uj minus 1n divided by 2h. The next two terms, I'm going to combine them as a over 2h, okay. I have uj plus 1n minus uj minus 1n, alright, and then I should subtract twice of ujn minus uj minus 1n. Right, this is that same term. Okay, and if you take a closer look, you see something really that you're suspiciously familiar with. So this is a over 2h. What is this? Is uj plus 1n. We get minus 2 ujn. For uj minus 1, you have minus 2 plus minus 1 plus 2. So this is plus uj minus 1n. Alright? This means, now I hope you see it, negative a uj plus 1 minus uj minus 1, that's the bad d0 guy, plus, if I write this as 1/2 ah, I multiply h, I divide by h squared, uj plus 1n minus 2 ujn plus uj minus 1n. What is this guy? That's just uxx, okay? So that means upwinding is solving ut is equal to negative a ux plus epsilon with same epsilon as the same concept of introducing epsilon as Lex Friedrichs, Lex Windroff, but for the different epsilon uxx. With this epsilon up is actually 1/2 ah. Remember in the last, we analyzed the eigenvalues of this form in the last video, okay? So when we have the epsilon, this, the stability region, this method of lines for this guy is here. The center, what's the center? The center is epsilon negative 2 epsilon delta t over h squared. Okay, that's the center. If you, for any epsilon, we did that for any general epsilon. Okay, this must be contained in the fold Euler stability region, which is a disk centered at -1 here. So, in particular, we want epsilon to be positive, right? So otherwise, the center of this ellipse is not even right. The ellipse will be on the right half of the plane. There's no way it can be inside that unit disk. Okay. So which means what? We have this 1/2 ah is larger than 0, which means a is larger than 0. All right. So that's a case we use uj minus 1. The logic here is that if using uj minus 1n means we must have a larger than 0 for stability, and vice versa. And when using uj plus 1 means the a is less than 0, right? So This also concludes that when a larger than 0, we use ujn plus 1 is equal to ujn minus a delta t over h, ujn minus uj minus 1n. When a is less than 0, we use uj plus 1n minus ujn a delta t over h, ujn plus 1. Okay. The last remark is about the size of this epsilon. Okay. If we define this lambda to be a delta t over h, we actually have the epsilon Lax-Winthrop divided by epsilon upwinding. This is, remember, Lax-Winthrop is 1/2 a squared delta t divided by 1/2 ah. That's lambda. Okay, but if we divide epsilon upwinding by epsilon Lax-Friedrichs, if you go back to the notes, you see Lax-Friedrichs is 1/2 h squared over delta t. This is also lambda. So lambda epsilon up is equal to epsilon Lax-Winthrop, which means this is less than or equal to epsilon upwinding, alright? Because this is lambda times epsilon upwinding. And this is less than or equal to epsilon Lax-Friedrichs, because Lax-Friedrichs is epsilon upwinding divided by lambda, divided by something less than 1, when lambda is less than 1 and larger than 0, of course. So upwinding is between Lax-Friedrichs, and upwinding is between LF and LW in terms of dissipation. In terms of dissipation, how much dissipation there is, how much diffusion you are introducing into the scheme.